G'day everybody and welcome back to the channel. So as I said in the last episode, in this one I'm going to shorten up these wires and make them out of proper link wire. The other thing I wanted to look at was this wire here that goes between negative and negative out. Sometimes adding a very small amount of resistance to it has a bit of a damping effect and helps. And the same thing with the emitter path of the comparator transistor. However, in this circuit we have a zener diode there, so there's still a few other things that I didn't point out in the last video. It's not just the snubber network in between the output and the comparator, but we're going to want to put some capacitance across the zener diodes. We're going to possibly add some very small amounts of resistance in one or two different spots. And we're going to do that to get it to, how do I say this? Not be able to oscillate. Not that I've had any problems with oscillating, but I mean, wouldn't be too hard to. For example, because the emitter of the comparator is looking at the output, if we moved it, let me just turn this off before I do something stupid. If we move it back here to the start of the circuit and I tap a load on it, I'll probably be able to get it to go into oscillation. Seems pretty stable. Okay. The zener diode must be damping it because of its dynamic impedance. I would expect that to oscillate. Maybe we'll get away without emitter resistor. I'm going to go off and do some thinking and calculations whilst I change these wires and come back, and then we'll go over what I've just said. Compensation networks, resistors, stuff like that. We're very close. Well, that's it. We've just got to go over those little fine tuning things, and then we'll start designing the board for this guy. So we're almost there. I'll be back soon. Measurement on this, I probably won't be, but here's something else I want to talk about. Actually, I was thinking about this. We fold back current measurement, because you're sensing a voltage drop across a resistor with a transistor using its base to emitter junction. Well, and the pot's a fixed value. How do I explain this? You could pretty much just run it without a screen and just write, measure the current output at different spots on the pot and write around the pot's pointer on the front panel the different currents, starting from the lowest to the highest. I could be wrong on this, but I'm thinking because it's a fold-back circuit, it's going to be, it's not like you've got to short the output to set the current limit, if that makes sense. I could be wrong, I could just be having a bad brain moment, but anyway, I think this is the circuit that I'm going to stick with. I've got the scope hooked up to it at the moment with this huge ground loop there, and I've got 970 microvolts RMS. I've got about 14 volts peak to peak, but to be honest with you, most of that is common mode noise because there's no common mode network on the output yet, and this huge ground loop. In fact, just doing that, I'm watching the peak to peak go down. So yeah, This is already quite quiet. It's going to be good. It's going to be a good build. I'm just going to have a look at the scope and pull this second stage capacitor out for the drive circuitry. I just want to see. Oh, okay, that does make quite a big difference. I think what I'm going to do is we're going to make that two-stage. Just like the original board had a two-stage capacitor circuit on it, filter. I think I'm going to do the same thing for this too. So I'm just trying to neaten a few things up for me and for you guys that are trying to see where things are connected and it's too messy. Alright, so 2.2K, I need to measure the voltage on this second capacitor and see how much below 24 volts it is right now with the load that's on it in order for me to calculate the two resistor values. Okay, 1 volt. So with 1K, we're missing 1 volt. I'm just trying to think if 22 volts will be enough, because I could add another K there. The thing is, that is essentially adding more. No, you know what? I think I'll do 560 ohm, 560 ohm, and 2 low ESI caps. That'll be adequate enough, to tell you the truth. We'll take this 1K out. I had a 560 here, I'm sure of it. What? I swear the oddest things happen in here. Wait, it's not on the board, is it? 560 ohm, no. Okay, that's really odd. I swear I grabbed one before. Oh, I know, I was going to grab one, but I didn't. So, I'm going to get two 560 ohms. I know, I should have paused the video, my apologies. I tried to hurry back. Alright, we'll put the first 560 ohm. Oh. Where on earth was that? I don't see an empty hole. Did I have two things doubled up, did I? I must have. All good. So now we're going to have to make this smaller like so. I didn't make it small enough. Okay. Now we're going to take our second 560 ohm resistor. I'm going to insert it here. I need to get a small link. I'm not going to worry about shortening those wires up too. I was having a think about that, and I can already see from looking at the scope, the performance on it is absolutely amazing. I will load it down and have a look at it too, but I just don't think I'm going to bother doing that. Just grabbing another one of these low ESR 100 microfarad caps, because I also didn't have that on hand over here ready like I should have. Alright. Now this can go a lot further back than what I put it. I really misjudged that one. Get in the hole. Good enough. Alright. This way we still have the same voltage, so we're not losing any current. Got a loose connection somewhere, I think. I somehow have more noise than what I had. What? Is it because I was lazy with my grounding? I didn't start ground. No. This is the thing about breadboard. It could just be something's a little bit loose. Don't know if any of these bloody resistors are 1K or 10K because the freaking markings just brown looks like red on them. That's a 10K, see what I mean? Oh, God. That's a 1K, I know that. I'm just going to put the 1K back in there. I'm just going to go get another 1K resistor. Alright, so we're going to be dropping a bit more voltage. Now we're back at the same as what we were before. So adding a second stage isn't really helping. It may underload, but so I'm going to go back to one stage quickly. Alright. Now my load bank is noisy, so what I think I might do is use this 10 ohm resistor for just a quick test. Alright, that's actually got quite a bit of ripple on it, so I go back to, oh, well, you know what? I haven't put my feedback networking. Dumbass Dave moment. That makes an insane amount of difference. So for that, we need space on the breadboard. We can do it down here. We use this spot for our compensation. I need to have a look at this capacitor too before I do that. What? What just happened? Now I've only got like 700 microvolts. Okay, that's what I mean about loose breadboard, you see. Alright, let me load it now. Even more ripple than the first time. Okay. Breadboard is hard to work with like this. Alright. We'll take a 104 to start with and a 100 ohm resistor. We'll put the 104 on the base of the comparator. Going back to the resistor. I bloody can't use these breadboards. Far out, man. I miss my old school breadboard. I just don't understand where you can buy good quality breadboards anymore. They're all bloody rubbish. And I hate it. You actually used to be able to build precision circuitry on breadboard, believe it or not. They had nice brass contacts and it's just, I don't know, everything was different. Alright, so that's that in. Still basically the same. Sorry about that. I heard a noise and it sounded like my cat was stuck in between two doors. It's happened before. I've just moved the ground back to here because this is so small it's causing a lot of noise when I load it. Now I can get a better idea of what's going on. Okay. I will show you guys the screen. I'm just trying to work out what's going to have an effect loaded versus unloaded. You might want to go down to about a 10 ohm resistor there. It's going to ruin the response timing of it though. It's not really making much noticeable difference. I might leave that network out. We can always tack on snubber networks on the board after it's etched up at the worst case scenario if needed. I'm going to investigate now this capacitor here. Oh yeah, that gives me quite a lot more noise. Now I've got 2.38 millivolts of noise. Well, you know what I should have done? I'm just going to leave this on the base. And leave this in positive. Oh, now that's my front door. I can't work like this. First cats, now this. I'll be back in a minute. Bloody hell, that wasn't even my door. That's my neighbour's. That's just them knocking on the wooden frame, because I live in a semi-detached house. Oh my god. I can't concentrate. Alright. So I have more noise with that out. Let's see if this network has an effect. Yes, it has a massive effect. Let me see what loading it's like. Then adding this. Quite an effect. Let me put my 100 ohm resistor back in. I'll show on camera once I've worked out what's going to have the most effect in this circuit, the differences, so people that are playing along at home can see. Okay, I'm going to need a 10 ohm resistor for there. I'll just pause the video whilst I go get that. Alright, you know what? I was going to get the 10 ohm resistor and I was literally walking over to get it, and I thought to myself, no, you know what? The boards, it's not possible to really do this with the board the way it is. So what I'm going to do, that does need to be in there. We're going to make up the circuit board now. I'm going to leave provisions on there for things. Oh, that's the other thing I wanted to do. Just quickly, I'm going to take a look at ripple with 1 stage versus 2 stage. I'll just do that off camera quickly. And that's all right, I'll do it on camera and I'll show you the ripple. Because I haven't shown anyone anything on the scope yet. That's because it's honestly pointless looking at it right now whilst it's on a breadboard. I tell you, these 1K resistors, alright. I want to see my voltage on the output because I'm not sure there's enough current. Okay. Okay, not much ripple at all. That's 2 amps, good. So with 1 stage, yeah, way too much ripple. Okay, we are going to do 2 stage filtering for the drive circuitry, and it's going to be 2 1K resistors. I'm just thinking, how much does that hurt regulation? 89, 99. It's not bad actually. It's about 200 millivolts with all this loss. Okay. Well, I think that'll do. I think that's the circuit we'll keep. So we'll get this etched up onto board. I'll draw the schematic out first. Oh, God. I'll get the schematic drawn out first. We'll talk about the schematic, and then we'll start etching the board, or designing the board, then etching it. And I'm just trying to think how I'm going to achieve this in terms of the video. So just to just to point out, sorry to interrupt myself, 18 volts is the top and the bottom will be 5.6. What am I missing? I'm forgetting something stupid here, I know. What is it? What is it? What is it? Was it? What is it? Is it my diode that I added here? Yeah, it's the diode. I guess it's alright. I wasn't really worried about this one going down to 0. I just wanted it to be a bit more adjustable than what it was and more useful, which it certainly will be now. So I could put the low reference diode down to a lower voltage, but the problem with that is I could also get the right value zener. Wait a minute, I'm having a silly moment. I've just put a wire in the wrong spot. Hold on. If I put this the other end of the diode, we should be good. That's my bad. Good thing I spotted that. There you go, 5.792. Wait, does that diode still have an effect on it? It shouldn't now. No. 5.7. I'm just trying to think. You know what? That's good enough. 5.8 to 18. I'm happy with that. More than happy. Although, you know what? Taking the feedback one diode junction away actually gives us just a little bit extra voltage, doesn't it? $18.08 and $18.06. Not really. Probably hurts regulation a little bit too. Because what I'm thinking is I wouldn't mind making it just a little bit above 18, so that if I've got a 2 amp load on it at 18, it can still be turned up to about 18. But I think honestly, after it's been turned on for about half an hour, it'll be inside a box too, so it'll be a bit warmer than what you see here. There'll be about, 18.2 volts eventually, close to it. It'll probably only drop to like 17.95 by the time it's all warmed up. So yeah, I think I might just leave it. It's good enough. Alright, that concludes that. What I'm going to do is I'm just going to leave all these components in this bowl here except for the 3055 transistor, because we're never going to use that. But the compensation components, and there's a few things that are left out of the circuit, like on the output there's also going to be a 1 microfarad monolithic capacitor in parallel to the electrolytic, and the same thing on the input. Or on the input I'll probably just put a grain cap on the input, a 100 nanofarad grain cap. But yeah, that's just to help get rid of diode switching noise, if anyone's wondering. Best to mount it actually on the diode bridge itself, but one on each side. But yeah, I might even just leave that out on this build. I'm not too sure yet. Or I might actually just stick a 1 mic mono cap on the input and on the output. I think that's what I'll do. So I'll do that, and on the board, like I said, I'll leave some provisions. So I'll leave basically a pad, a trace and a pad coming off the base of this transistor, the comparator, going to, a pad that goes to you can put a resistor there in series with a capacitor, and then that will go to a trace that goes to the positive output. And I'll also have two traces with two pads coming off this transistor for this capacitor to be mounted there, so that we can change the values of an RC network and a C. And that's all we're going to need to change, to be honest with you. So yeah, that's it. And bear in mind, what I'm seeing on the scope, what I was saying, actually I never showed anyone. This is with this big ground loop and no common mode network, so don't focus on the peak to peak too much. But that's 800 microvolts RMS. It'll be down around 500-ish, maybe 550, 600 once it's all on a board, short wires, lower resistance wires, all that sort of stuff, good connections, and then we'll adjust those compensation components. You know what? Another thing I want to have a look at quickly, and I'll do that in this video, not the next video. I'm just going to get a 1 microfarad MKT capacitor. I'm just going to hold it across the zener whilst I'm looking at the scope. Problem is there's another diode here too. I'm not sure if there's switching noise on it because of the zener in series with it, so I just want to try across both. That actually makes quite a difference. We go from 750 microvolts to 850 microvolts. So let me just check this one. That makes it noisier. So I'll put a couple of pads coming off the zener diode for a compensation capacitor too. Just thinking, it's going to go across both those diodes. It was quieter when I put it across the entire pot. There should be, actually that's something I forgot. There's supposed to be a capacitor across the pot anyway. Anyway, could put one across the wiper and the positive of the pot too, and see if that, oh no, we already tried that. Yeah, well, alright, I'm done playing around with this. I hope everyone's got a little bit of an insight into designing a little circuit like this. Watching me build it, you get to see, I'm not talking about my mistakes like choosing, not realizing that there were PNP transistors in there and stuff like that. I'm talking about all the little design considerations. I hope that helps people that are learning, give you a bit of an idea as to the thought process behind designing something. So, yeah. Actually, that's not really coming up much past 1805, is it? You know what I'm going to do? I'm going to hook my scope probe up one more time. Sorry. I want to see, when I load it, if taking feedback after that first diode affects performance in any way, both on regulation and on noise. Got a funny feeling it might on noise. Oh, I can already see a crap ton of noise just like that. Okay, cool. That diode seems to be blocking some of the zener noise. Oh, it wasn't that. Yeah, it's my load bank. Bloody hell. No appreciable difference. Alright, cool. I'm done playing around. I'll just show everyone a quick look at the waveform. Sorry, I keep forgetting. I keep saying I'm going to show you, I'm going to show you, I'm going to show you. I showed you unloaded, I didn't show it loaded so people could see the difference. Where's my bloody voltage gone up? Oh, at the load bank. So when the load bank's attached, there's some noise from the load bank, but the thing I want to show you is the fact that, oops, when it's loaded, there's not much increase in the waveform size, and all those spikes will be gone with the compensation networks and the other styles of capacitors that are going to get added, and it all being on a board and all that. You'll be quite surprised how clean this will be. Plus we've got this ground loop here, so I'm quite happy. This is going to be great. So I'm going to draw up a schematic for you guys now, and then I'll come back and I'll go over the schematic with you and we'll talk about it, and then time to start making up circuit boards, or a circuit board. I just wanted to mention I'm going to Bunnings tomorrow, so I was going to cut out the front panel and do all that work today too. That's not able to happen till tomorrow, so basically today is just going to be about the circuit diagram and getting a start on the PCB, or I might do that in a separate video because that'll take a bit of time. But yeah, the case cutting out, I'll get that done off camera anyway, but that you won't see in this episode, or maybe the next episode, but definitely the one after. Alright, so I'm just about to draw up a schematic, but I just wanted to address two things, and I'm going to show this on camera. Well, I'm not going to show it on camera now because there's really no point, but those spikes that you saw when I loaded it down, they're from the load bank. I just wanted to point that out. And the rest of the noise, the peak-to-peak noise, is from all the loose stuff on the board and the ground loop and all that, and the lack of common mode filtering on the output, and so that'll all be gone. Anyway, the main thing I want to address before I draw a schematic was this transistor here, the tip 41C. I put that in there when I was designing it, just because it was a what do you call it, easy to grab, common, very common part, but it's actually way overkill for the job. So what I'm going to do now is I'm going to calculate how much current these transistors need, the 3055s, to be driven, and work out what I can use in there, because that's way more current, way more voltage than what we need. And we might be able to find a small transistor with more gain, which will be even better in this circuit. So I'm going to go do some calculations and I'll be back. I've just set up to take some measurements. What I'm going to do is I'm just going to pause for a second, put the phone in the tripod. This way I can show you the setup and I can show you the scope, which is looking quite nice at the moment. If I can just get that to focus, yeah. And that's with the load bank plugged in. Let me just unplug the load bank quickly. You'll be quite surprised. It's creating a lot of noise. That's without the load bank. That's about 850 microvolts RMS and 7.8 to 8 millivolts peak to peak. And I'm just going to prove something else. I'm just going to put the phone over here. What's the best way to do this? If I just grab a short clip lead and go to the case here, which is earth. And I'll just grab one of these 1 microfarad capacitors. I'm just resting it there on the positive. We'll just come back here and have a look. And we see now there is 485 microvolts RMS and 5.2 millivolts peak to peak. This is what I'm saying about by the time this is on the PCB and there's a full common mode suppression network on the output that doesn't just go back to the case and blah blah blah. Trust me, this thing will be bloody quiet. Every power supply I build is quiet. I'm just one of those people that likes quiet supplies. Anyways, and that's without compensation. I mean, there's 2.2 nanofarad compensation capacitor, base to collector that is, on the comparator transistor. So that doesn't really slow down the response timing of it like the capacitor going from the feedback to the base does. So not only it's quiet, but it's quite responsive. Might not be the most accurate thing in the world, but that's the thing. We're loading it down quite a bit. I'm putting 2 amps on it at 18 volts. Oh my god, I'm getting another cold. I can't believe this. And I've got so much I want to get done the next few weeks. I usually only get colds for a day or two anyway, so I should be alright. But if I can find somewhere to clip on. That'll do. So I'll just hook my load bank back up. Back up at 18 volts. If I just put, say, 1 amp, which is pretty much what I'm designing it for at 18 volts, to do at 18 volts, 1 amp makes it drop just that bit. So it's not too bad. And like I said, the regulation is going to be even better when this is all on a circuit board and in the box and we don't have volt drop across wires and stuff like that. You'll be quite surprised. Yeah, so what was I going to show you? There was something else I was going to show you too. Oh, now that we've cleared up why there's extra noise on the screen, I just want to show you, because now you can understand that half of that's not really there, it's the load bank, right? I've just proven that. Now I'll put the 1 amp load on 18 volts. Those spikes are the load bank. And I can prove that because if I unplug the load bank, alright, and I'll just grab a 10 ohm resistor out the drawer. 10 ohms at 18 volts will be 1.8 amps. that is more than the 1 amp I was putting on it with the load bank, and I'm going to do this like this, right? Okay, the spikes actually are from the supply. There you go. I did not know that. That's fine. We'll sort that out, like I said. That's just because we've got long wires and stuff like that, to be quite honest with you. That will go. Especially with the common mode network on the front of it. Shorter wires, PCB, all that sort of thing. But as you can see, that was close to 2 amps to 18 volts. So it's not doing bad. Considering it's on breadboard, this is the thing you've got to remember when you're designing stuff. Breadboard is wonderful for prototyping, but at the same time it's terrible. As long as you can remember it's terrible, you'll be alright, because basically what I'm trying to get at is just design your circuit to perform good, but when it doesn't perform as good as you expect it to, just be aware that that's the breadboard, not your circuit. And once you start getting used to that, you'll be alright using breadboard. It's kind of hard to explain. You get a feel for it. You get a feel for what the breadboard's doing and what your circuit's doing. It's just one of those things. Alright, so I'm going to turn it down to, let's go to 12 volts. Put 1 amp on. Okay. Alright, I'm going to go 2 amps, 3 amps, 4 amps, 5 amps, 6 amps, 7 amps, 8 amps. Alright, 7, 6, 5. Okay, so it's when I go past 5 amps on the scope, 4, 5 amps on the scope, that it starts getting noisy. But that's only mains ripple, not, I'll show you, you'll watch. See how all of a sudden you get that and it goes nuts? The reason for that is, again, there's nothing wrong with it. It's just because we've only got a 4700 microfarad capacitor. When it's in there with the 14,000 microfarad capacitor, trust me, that won't be a problem. So I'm at the point now where I'm ready to basically draw a schematic. Oh, sorry, there was one other thing I wanted to do, and I was going to do it on camera. I'll just unhook the multimeter because everything's getting a bit tangled here, and the worst thing is when you've got too many wires everywhere, you trip or knock one and it pulls something out when it's switched on. And with a circuit like this, certain things can go open circuit and smoke transistors. You don't want that to happen. Right, so what I want to do, I don't need the scope anymore either. I've seen all of this before, but I didn't show you guys very much earlier on when I was still building the board. It's kind of hard for me to sit there and go backwards and forwards between the scope and the board, but now we're done, I thought I'd give you all a look. Like I said, it's going to be a lot better when it's on PCB and the rest, the compensation networks and the common mode filtering's done and all that. Tons better, and it's already good, as you can see, so that's good. What we're going to do now, I'm going to put 6 amps on. It's at 10 volts. I'm just going to turn it up to about 12. Let's see how much heat the tip 41C is generating. Oh, I might actually just turn it down as far as it can go. Now I might just turn the current up to 8 amps. series pass elements, yeah, they're warming up. They're doing good, but actually that tip 41's starting to get hot, so no, I'm actually going to leave that. I don't have any other transistors with high enough gain and current handling that have a lower voltage, if that makes sense. So we're just going to keep that in there. That's perfectly fine. So that's basically all I wanted to do, really, was show a couple of things on camera, do that one last little bit of working out with that transistor. Now what I'm going to do is I'm going to stop the video. I'm going to draw a schematic of this, and then I'm going to show the schematic. That way everyone can understand it. I think most people that are watching that have a basic understanding of electronics will be able to understand this just from watching the video, because I built it in front of you all. But for people who are trying to learn, I'm going to draw a schematic just to make it easier for you to understand. I hope that helps. If anyone's got questions, leave them in the comment section. I'm more than happy to explain anything that you want to know. That doesn't bother me at all. Even if you ask me a really complicated question and I can't answer it, I'll go and do my own research and find the answer for you. You know, because something I like is learning, and that's the good thing about electronics, is you're always learning new stuff in this trade. You can never learn it all. I'll just say that. There's always a new corner to turn, a new page to turn, however you want to word it. There's always something new to pick up, and that's what makes it so interesting. Alright, I'm going to stop the video and get to drawing now. Okay, I've made a couple of changes. Excuse me, I'm getting a really bad sore throat. I'm getting another cold again, one sec. Oh, yuck. My throat hurts, feels like sandpaper, and I can't stop making phlegm. It's just... it's really odd, because I usually get like one cold in 4 years, and I've had 2 in the last couple of weeks. Good luck to me. Anyway, the 1N4148 diode's been changed for a... Sorry, the 1N4007 diode has been changed for a 1N4148. Excuse me. My throat's really giving me trouble. And what else have I done? Oh, I've also checked the value of this 2.2 nanofarad capacitor. I've gone down to 1 nanofarad and gone up to 4.7 nanofarads. 2.2 nanofarads is bang on the value it needs to be. Excuse me. So what I've gone and done is I've drawn up the schematic, and that's what we're going to take a look at now. Incidentally, that voltage isn't like that because the diodes have heated up. The benefit of having the 4148 diode is it has a higher forward voltage drop. How do I explain this? With a smaller amount of current passing through it, because it's a smaller diode. So as soon as I turn this on, even when it's cold, like, I'll leave it off for a bit. Just got a brand new mic insulator, and I just blew it away. Got hundreds of them, but still. Right. You see it's already above 18. Before it was just shy of 18, so that helps there. Alright, so I'm going to move this to the side because I need to get the schematic here. I'll just pause. Okay, so what I've done it on 2 pages for people that are learning, just to make it easier, and because my drawing is shit. So what we have is, on the line side, live side, whatever you want to call it, switch. Actually, you know what? There's my first error. Swap those two around. Fuse, then switch. Then we've got our transformer going back to neutral. Now, you know something I actually forgot. I feel like I spelled that wrong. I think it might be 1S. Anyway. Alright. Ground goes to the transformer. It also goes to the core, all of the steel around it, including the band. Then over here we've got our rectifier, our huge 1400 microfarad cap, a 1 microfarad monolithic capacitor. At this point we now have 24 volts DC. 2 100 microfarad low ESR capacitors, 2 1K resistors. This is the positive for the driver circuit. This is the positive for the series pass collector. This is our common negative and our ground. So that's the power supply for the power supply. It's always funny when you're building a power supply, because when you're building a power supply, you have to build a power supply for the power supply. And if you're building a more complicated power supply, you have to build multiple power supplies for the power supply. I just find that funny. Anyway, moving on. So we've got our series pass element. We've got 2 1K base to emitter resistors, 2.1 ohm emitter resistors, and 2.2 ohm, 1 watt resistors, all the resistors in here, other than what's noted, are half watt, 1% metal film. All right. We have 2N3055s. Here we have all the other transistors. Is this on camera? Now it is. My apologies. Right. All the other transistors are BC547s except for this one. This is a tip 41C. So 1K base to emitter resistor, 4.7K base to emitter resistor, no base to emitter resistor on the last one, 1K base resistor. Coming from the positive driver feed, a 2.2K resistor. Now, everywhere that there's question marks next to a component, it's because we don't have the component installed yet, and not until it's actually made up on a board with the correct lengths and thicknesses of wire and all that in the case, we can't put those values in, because we have to fine tune them on the scope under certain conditions when it's built. For example, we might not need this one, we might need it. We might need this one, we might not. We might only want a capacitor here, we might want a capacitor and a resistor. We might not want either. Here, we definitely will want a cap here and here. It may go to a resistor, it may just shunt to ground. So that's why there's those two options and a question mark on each. And the value of the cap could be anywhere from 100 nanofarad to 1 microfarad. So again, that's what all the question marks are, right? 2.2 nanofarad disc ceramic, another BC547 like these two, 5.1 volt zener diode, 5K logarithmic pot, half watt will do. 12 volt zener diode and a 1N4148 diode. Oh, there's my second mistake. Whoops. That's better. 12 volt zener diode and 1N4148. Here we have a 200 ohm 5 watt wire wound resistor, a 470 microfarad low ESR cap, a 1 microfarad monolithic capacitor, and a 1N5822 Schottky reverse protection diode. So that is the whole circuit. Like I said, excluding things that we're not sure of yet. Actually, I meant to also put a line in here with a question mark because, yeah, these are all things we're not sure of yet until the board is made. So that is what the next video will be. The next video will be making up the board, etching the board and populating it and putting it all together. And then the video after that will be basically loading it and compensating it with said components and looking on the scope. And hello, little man. Daddy's busy now. And that will be it. That will be the last episode. So I'd say we have, what are we up to? Second episode? No, third? Probably be 5 episodes, 5 videos. So there you go. So that concludes this video. I've gone over everything I wanted to go over. That is the final circuit. Well, let me say this. There's these components that we have to work out the values for and if we even want them. Also, if I end up adding fold back current limiting, I'll just draw that circuit on another page. Basically, it means we'll have to insert a resistor in this line here, and there'll be a transistor sitting here looking at the resistor and the base of this. I'll show you guys when it comes to it. So it might be the base of the comparator. I can't think right now. It's literally 2:22 AM. I just really wanted to get this video finished for you guys. So that's that. Again, if anyone has any questions because they want to build this themselves, feel free to ask me. If you have a different transformer and you want to know component values, if you can tell me the exact transformer, you know, volts, amps, you know, if you get me a data sheet, tell me the transformer so I can look at a data sheet and work out how it runs. That'll help me, and I'll be able to adjust values and, you know, suggest some values to adjust in the circuit. But yeah, other than that, that's all I've got to say. So I'm going to leave it here, and I'll see you all in the next video. If you like the content, please like and subscribe, and jump down below in the comment section and chat away. Thanks for watching.